So we will code a simple diffusion model training, and you don't need any pre-existing knowledge except maybe Python, a bit of mathematics. If you know some AI stuff, it's good. And by the end of the video, we will train this model, have this loss here, and we will train it to predict noise. So diffusion model is used in Google VO3, Stable Diffusion, Midjourney, and then Gemini Diffusion, and a bunch of different areas, LLMs, and visual image generation, video generation. Diffusion model is a type of generative model. So it's a generative model. It learns to create data like images or numbers or words or tokens by gradually removing noise from a very noisy input. So we'll see what that means. So there are two parts. For word process, we add noise to a clean input over time. So this is during the training. And reverse process, a neural network learns how to undo that noise step by step. So this is training. So we prepare. So we add noise, and the neural network learns how to go backwards, remove the noise to get the clean image. So that's during training, and then during inference, we can just start with any random noise image, and we can use this reverse process to generate some image, and we can condition that on text. So we can couple those images with text as well. We'll begin with just one number, x0, like a toy image with 1 pixel, and show how noise gets added to it over time. Okay, I adjusted my microphone a little bit. So step 2, noise schedule. A noise schedule decides how much noise we add at each step. So first we add a bit of noise on the image, only a few dots. Then we add a more, and in the end, the whole image is all pure random noise. This is an example. We have an image of a cat, we add a bit of noise, and in the end it's pure noise. And this can be 1,000 steps, it can be 4 steps. In the beginning it was like hundreds or thousands steps, but later as technology progressed, we just need fewer steps, so it's faster to compute. There are new techniques to do this. So it uses a variable called beta t to represent the variance of the noise at time t. Let's see, we have numpy, we have this pie plot. So t is the total number of diffusion steps. So we got 3 diffusion steps here, but let's start with 1,000. Here, 1,000. It says this is like how many frames. I don't know what ChatGPT means by frames, but it's just what I explained. We define the starting and ending amount of noise. Small at first, large at the end. So this is starting amount, ending amount. We will just give these numbers. So we'll see later what it means. So this is a small number, this is a big number. Linearly space the beta value over time from start to the end. So going from this number to this number, there are 1,000 values in between, or in total there are 1,000. And then each value is linearly spaced between these numbers. So just divide this space, and each distance between each value is equal. So like we define start and end, and then in between everything is linearly more noise than the previous image. This is an example. Starting, ending, and everything in between is linearly spaced, although it looks like here there is a big jump. Maybe this is not so linear, but you get my point. Then convert beta to alpha, which is how much of the original signal remains. So in the first iteration, you can add 1% noise. And you will have 99% clean image. And in second iteration, you add 2% noise. Now you add those 2% onto the clean image, not onto the whole image, but only onto the clean part. So now you multiply them to get the actual clean image now after the second step. So 0.97 is the clean image, 97%. So that's why we have this cumulative product. Cumulative product of alphas tells us how much original signal remains after t steps. So they call this alpha bar. If alpha bar is 0.8, 80% of the original signal is still present, while 20% has been replaced by noise. Step 3, forward process, adding noise. Here's the key idea. We add noise to our original number, x0, in a smart way so that we can reverse it later. So let's take a look at this formula. First, this alpha t is how much of the original clean image is remaining at step t. So this is the clean image. x0 is our initial number or image. xt is noisy version of timestamp t. So xt is this image with noise and with clean space. So this entire thing that we get at this step, image with noise and clean space. And then epsilon is just a random Gaussian noise. This is what we will add this noise. It will be just some random numbers. It's a way to sample a noisy version of x0 directly at step t without simulating all the steps from 1 to t. So you can directly simulate noise at step t. So instead of doing this, x1 is noise of x0, x2 is noise of x1, etc., we can jump directly to timestamp t using this one formula. So why do we need variance? To measure how much noise we added. At time t, we want to say this is 75% signal and 25% noise. In probability, we express this using variance. Signal variance 0.75, noise variance 0.25. So we make sure the signal and noise components add up to 1, total variance. To give everything Gaussian, we want the whole distribution of xt to still be a normal distribution. This means we need to set the variance correctly, or it's no longer Gaussian. So what does it mean for xt to be a normal distribution? So it looks like this. Normal distribution of mean and variance. It means most values are near the mean. Spread is controlled by the variance. The distribution has very specific shape. It's a bell curve. In diffusion, xt is not just a number, it's a random variable. So I guess if you don't understand, maybe you can ask ChatGPT or ask whatever questions you have. In our code example, we'll simulate a simple 1D image, which is just an array, like a sine wave. So here, lean space, this is a sine wave, here x0. So just imagine that these random numbers, doesn't matter if it's a sine wave or not. Then define noise schedule, betas, how much noise we add per step. Here, we just explained this code. So we have number of steps and then noise per step going from low to higher. And then these alphas are just a clean version, and alpha bars is the cumulative remaining clean space on the image. So then we just apply, we write this formula that I explained. So this is the alpha bars, and this is the noise, so it's just a random numbers in this shape of this vector, input vector, so we can apply this to it. And then just the formula that we explained, return the noised version and the pure noise as well. So this is what it looks like. We are adding noise. So the black one is our original tensor or vector. And then the blue one, it's coinciding in the beginning because there is no noise, T0, there is no noise. So blue and black are same. And then orange, a little bit of here noise, you see a little bit. And then green, more noise. And then red, the most noise. Because red is at time step 99, so most noise is added. Next, let's code the training objective for the diffusion model. We'll simulate what training a diffusion model looks like. Goal: train a neural network that predicts the noise epsilon from a noisy input xt. So if the model learns this well, we can later use it to denoise. But we'll see what this formula means, don't worry about it. Step-by-step plan. Generate training data, so x at beginning, so this is the input vector that's noised, epsilon and t time step, so this is the noise. define a simple MLP multi-layer perceptron model, for example, 2-layer neural network. So we are just training it to predict the noise. So, and that's gonna be our loss. We measure the difference between predicted and real noise, and that's our loss. And when we have the noise, we can subtract noise and get the real image, the real vector, the real numbers. We have exactly the same setup. We have this sine vector, and we convert it to torch tensor, and that's it. And then diffusion setup is same. And then below, the same function to create noisy data. So we will create the noisy signal and the noise itself. So we will return both of them. And then define the model. We'll use a simple MLP that takes xt and timestamp t and predicts the noise. So noise predictor, it's gonna be an NN module. It's a sequential model, the network called the linear. Input dimension +1. We'll see why +1. Converts to this middle, and then ReLU, and then linear goes back from this middle dimension into input dimension. And then the forward will be normalize t between 0 and 1 and expand to match batch. So let's explain that. So we want to train a neural network to learn this mapping. So X, so noise version of the image, and timestamp mapping to the noise. So meaning given noisy version of the data and the diffusion step t, the model should output the noise that was added. We do this because during generation we'll reverse this process using these noise predictions to denoise, to generate a new image. We will just start with some random noise and generate a new image. I explained this noise predictor noise already. So why input dim +1? Let's say input dim is size of your data vector. For example, 100 points in a 1D signal. So xt has shape 100. So this is 100 points in, let's say, 100 just numbers in a vector. We also want to give the model the timestamp t, because the model must know how noisy the input is. So this 1 is just the additional timestamp. So early t, slightly noisy, only a little noise to predict. Late t, heavily noisy, and mostly guessing. So we append t as an extra input like this. xt value 1, xt value 100, and then t in the end. So this is the actual input. So we just appended. So input size is input dimension +1. So this is size of your vector, you know this. What is input dim? So it's gonna be the shape of our x0 vector. So example 100. Why normalize t? So you see this is in the forward. In forward pass we normalize t, the first thing we do. This maps timestamp t from 0 to t to 0 to 1. So if we have 100 time steps, we will map that between 0 and 1. So it's gonna be, instead of 1, it's gonna be 0.01. Why? Neural network learns better when inputs are in a reasonable range. So usually you want to normalize between 0 and 1. So feeding raw t like 98 or 32 makes learning harder. Normalizing value helps the model generalize. It just makes numbers more stable, and there is no big numbers or very small numbers or very huge numbers, etc. So numbers between 0 and 1 are very stable. So there is no like very small number somewhere that gets cut off because it can't fit into memory, or very big number that also gets cut off. This is the forward pass. So it is a bit tough. So I'm just gonna quickly explain, and then we will do some exercises so we learn and practice what all of these operations do, how they transform these tensors intuitively. Firstly, normalize t. So between 0 and 1. So we have some batch size. So let's say we are processing 5 independent examples or images at once instead of 1 by 1. We have, like, let's say 5 of the timestamps. So we just want to expand from this dimension to this dimension. It will just be like additional, like this square bracket, and like this it will be like this, but it will be columns. Yeah, we'll see. We'll practice this. So next, concatenate along feature dimension. So we just go from here. We will concatenate the x. So we have number of batches, and for each batch we have input dimension of our sample and one more for the timestamp. And we will practice this and then pass through network. We will just pass this through the network. So let's see what actually happens there in more detail. Let's say we have batch size is 3, so we have some 3 images, so 3 independent examples. Each of them has 4 numbers. And then total diffusion, so this is the dimension of each image. Let's just say it has 4 pixels. And total diffusion steps is 100. So step 1, I will just show you here, for this explanation we are creating this example data. So this is example data, first image, second image, all independent. And we will add noise to all of them independently. And then the timestamp, it will just be some vector of 3 numbers. So meaning sample 1 is a timestamp 25, sample 2, so this is sample 2, it's timestamp 60, and 3 is 85. So this is noise at this step, noise at this step, and we will calculate that. So normalizing timestamps. These are raw from 0 to 100. We want to normalize them, so we will divide this by the maximum, which is 100. So we get actual these values now for timestamp. This is just to normalize it for training stability. So then we will add a dimension to this with unsqueeze 1. So after unsqueeze, you see what it looks like. Those are columns. Yeah, there is comma here. So those are rows, I mean. There is 1 column with 3 rows. That's what unsqueeze does here. So this will be for each of the examples here, each of the samples. We will just transform them like that. So now we can concatenate them because this was just a one array. So then we have this torch cut concatenate. So we have this, we will put it into an array, and in the array there will be this first tensor, and in the end t normalized for each of them. So this is amongst dimension 1, inner dimension. So that's why we will just get these tensors. We glued the timestamps to the end of each sample's features. Dimension 1 means concatenate along the feature dimension. So now each row has 5 values. So the feature dimension is like these numbers dimension. And then we also have this explanation, what the neural network sees. So neural network will learn that the fifth one is the timestamp. So if the fifth one is large, it will learn that it needs to predict a lot of noise. If the last one, in this case is fifth, is low, then it will learn to predict only a bit of noise. So if the timestamp is 0.25, the network thinks this data is 25% noisy. So this is just bonus. If we try to concatenate along dimension 0, it will throw an error because we unsqueezed, so it matches, the dimension 1 is gonna match. We want to add features columns to each sample. Keep the same number of samples rows, go from n input to n input plus 1. We can also take a look at the full training code. So this was written by Claude. It's very good, it's correct. So this is the same thing. You can, if you want, you can check, but we already explained all of this. Adding noise and stuff, generating some data. Everything is already familiar, and this is the neural network. There is more of the layers now. and the forward pass will be the same. And then the training, we specify model optimizer, loss, etc., and just loop. So this is just for visualization. So let's see first the visualization. The training loss. So I trained it for like 5 minutes, 10 minutes. I just made some like random numbers and then noise, and then try to, or not random, it's like this is clean signal example. And then the noise is like this. So the training loss goes down. Noise schedule, you see, signal is going down a bit over time, and noise is increasing as the time step increases. And here we see at the time step t10, so the blue is the true noise, and this orange is predicted noise, and you see it's actually predicting quite well. Time step t25 as well, t40, so you can see that at each time step it's predicting noise pretty accurately. This is the training, and you see the loss is decreasing, and already in the first 100 iterations, 100 steps, it already converged or got a lot closer to the final value of 0.29. So the biggest improvement is in the first 100 steps. Here you can see this other information, but and okay, initial loss, final loss improvement 69%. So that's a small diffusion model from scratch. You can check my other videos on my channel to learn more, and see you next time. We will learn more about AI science engineering models and stuff.